Before we get into dividing complex numbers, please be sure that you've gone over how to find complex conjugates. You will need to know complex conjugates for dividing complex numbers. Given that you've known that, though, let's go on to find how to divide complex numbers. Now, similar to dividing with variables or with radicals, you're basically trying to find places where you can cancel or reduce. At the same time, remember that I is a radical, and you can't leave a radical in the denominator. So basically, we're just trying to divide out different factors from the top and the bottom of our division problem, or our fraction, basically. So in our first example, again, this is a division problem, but we write it like a fraction, 4i divided by 6i. Well, notice we can divide out I from both pieces here. Now it's basically just 4/6. We can divide 2 out of each of those, so it becomes simply 2/3. That's really it. All we're doing is just recognizing the pieces that we can divide out and reduce it down. So in this case, we have 12i divided by 9. Well, we don't have i's in the numerator and denominator to cancel out, but in both the numerator and denominator, we can divide out a 3. That way we would have 4i over 3. Now you can leave it as 4i over 3, or you could recognize that as 4/3 I. Either one works. Just like how we can say 4x divided by 3 is the same as 4/3 x, this I can kind of be brought out here to say that it's 4/3 times I. Now in this case, this is basically the same exact problem as over here, only I added a negative at the bottom. Now again, I can divide out a 2 from the numerator and denominator to leave a 2 and a 5. And for some reason, I guess I divided out a negative 2, so the negative came up top. Please note that this negative could have also been down here, and it would mean the same thing, right? Negative over positive is the same as positive over negative. So again, like we did over here, we can take the I out and call it negative 2/5 times I. Okay, they all mean the same exact thing. It's just a different way to simplify or reduce this this complex division problem. Let's go over some more examples. Now before we move on too far, I want to make sure that you can remember this about fractions. If I want to change 2/3 into 12ths, so I need to get 3 over to 12, I multiply the entire thing by 1. Right? 2/3 times 1. Now 1 comes in many different forms. One way to say 1 is to turn it into a fraction, 4 over 4. Right? So when I'm doing this, multiply the top and bottom by 4, I'm actually just multiplying everything by 1. So 2 times the 4 makes 8, 3 times the 4 makes 12. So 2/3 times 1 is 8/12, meaning this and this really aren't any different. So I want you to think of that same idea when we're trying to get this one reduced. 1 over 9i. Now remember, I is a square root. It's the square root of -1. And we can't leave a square root in the denominator. So we also can't leave I in the denominator. So to get rid of I from the denominator, we're going to multiply the top and bottom by I. When I do that, 1 times I is just I. 9i times I is 9i squared. Now again, remember, I squared is the same as saying -1. So 9 times -1 would be a -9. So 1i over -9. Now again, like before, we can move this negative up to the top. We could also, if we needed to, move it out front, or we can call it -1/9 I. Any of these will work. Here's where complex conjugates really come into play. You need to know your complex conjugates to be able to simplify or reduce this division problem. Now, remember, this whole thing on top, the numerator, is grouped together to make one complex number. Similarly, on bottom here, this is grouped together to make a complex number. So the real part, 5, plus the imaginary part, 2i, this is all one complex number. Same thing, 4 minus 3i, complex number. When we are dividing, we need to think of these as just one number, right? Binomial over binomial. Now, we can't just divide this one by this one, or this one by this one, because this is all one number on bottom, just like this is all one number on top. However, because we have this I in the denominator, we need to get rid of it. We can't allow there to be an I, because, like up here, this I is the square root of a -1, so we need to get rid of it. Now, how do you get rid of the whole binomial on bottom? This is where complex conjugates come into play. Instead of 4 minus 3i, we multiply the top and bottom by 4 plus 3i. Now when you do the top and bottom multiplied by the same number, again, that's like multiplying by 1. Here, here, and here. These are all examples of multiplying our fraction by 1. Now in this case, let's look just at the denominator. So I'm going to block out the numerator for just a second. We're multiplying our denominators together. 4 times 4 is 16. 4 times 3i is 12i. Negative 3i times 4 is negative 12i. Negative 3i times positive 3i is negative 9i squared. Like we saw before, our I terms are going to cancel out. So we're left with positive 16 minus 9i squared, but I squared, remember, is negative 1. So instead of minus 9, it now becomes plus 9. So 16 plus 9 is just 25, meaning our new denominator is just simply 25. So we multiplied the top and bottom by 4 plus 3i. Our denominator simplified nicely just to a 25. Notice there's no more i's left, it's just a constant. Now we need to do the same with the top. 5 times 4 makes 20. 5 times 3i makes 15i. 2i times 4 makes 8i. And 2i times 3i makes 6i squared. So now we have our numerator and our denominator. This numerator can still be simplified though. So 15i and 8i make 23i. I squared makes negative 1. 6 times negative 1 is negative 6. And negative 6 plus this 20 would become a 14. So it's 14 plus 23i all over 25. This would be your simplified division problem. We went from complex divided by complex, where we had a radical in the numerator. We used our complex conjugates to get rid of the radical in the numerator and simplify it to a fraction that had a whole number or a constant in the denominator. Let's try a few more examples. Okay, we're going to do a very similar problem, complex number divided by complex number. Again, remember, the trick here, multiply by the complex conjugate to the top and bottom. Now I'm going to put parentheses around this to help us realize or recognize we have a binomial times a binomial. Binomial here times a binomial here. First, let's work on the denominator. 3 times 3 is 9. 3 times 4i is 12i. Negative 4i times 3 is negative 12i. Negative 4i times positive 4i is negative 16i squared. At this point, our I terms cancel, and we're left with 9 minus 16 times negative 1. I squared became negative 1. Minus 16 times negative 1 becomes plus 16, and 9 plus 16 is again 25. So our denominator simplified to 25. Now we FOIL the top. 5 times 3 is 15. 5 times 4i is 20i. Negative 5i times 3 is negative 15i. And negative 5i times 4i is negative 20i squared. We combine these two I terms to make 5i, and this I squared becomes a negative 1. Negative 20 times negative 1. This goes away and basically becomes a plus here. 15 plus 20 would make 35. So our numerator is 35 plus 5i. All over our denominator is 25. So this would be the simplified form, except for the fact that if you look at all three terms, 35, 5i, and 25, we can take a 5 out of every single piece. It's kind of like saying we're going to factor the top and take 5 out, leaving 7 and 1i. Now we've got this binomial times this coefficient, and down here this is the same as saying 5 times 5, and we're just going to divide out the 5 from the top and from the bottom. That way we can see, okay, we have simplified. We're dividing out 5 from everything. 7 plus I, or 1i, all over 5. So when you get it down to even this piece, let me get my eraser. When you get it down to here, check and make sure that if you can factor out a certain piece and divide it out of this one to simplify, make sure you do that. This is the most simplified form of our complex division problem. That'll cover it for our final video. Remember, here we discussed using complex conjugates to divide our complex numbers, and we talked about how to divide complex numbers even without those complex conjugates.